Hello and welcome back to compiler programming. In this video, what I thought I do is start working towards correctly layouting our functions in memory. Because what is happening right now is kind of bad. Let me open up this painting program so I can do a bit of explanation. Right now, when we create a function, so let's say we have function A that we are compiling, and we have function B. Every time we start to compile a function, we call to Windows, and it gives us some random location in memory. So imagine that here we have this gigantic memory, and it contains a bunch of addresses. Oh, I really can't do straight lines apparently. So let's just say, oh, this is not what I wanted. Let's just say we do it like this. And it's just a gigantic array where we can store byte. So we can ask Windows and like, give us a bit of memory that we can use to store the function. And the Windows like, sure, here's your memory. Let me change the color maybe. Here's your memory. Something more brighter, like so. Okay, you can have this. So Windows checks here and gives it for us to use in A. We're like, okay, now we're gonna do B. We again ask Windows, okay, what is the memory that we can use? Windows is like, well, you can use the memory right over here. And gives that back to B. And if you think about it, like between this memory over here and this memory over here, there can be a lot of space. Like there's a bunch of stuff that is happening. So that means that no matter how small or big function A is, the CPU will never have it in cache nearby, right? Because CPUs usually load memory into cache, thinking that you would use subsequent bytes. So even if they try to preload next thing in memory when they are moving in certain direction, including the instructions. So it would be nice for just this purpose, even though we are not thinking of optimizations, if we did this layout ourselves. So what we want to do instead is when we at the very start of the program, the first thing we do is we ask Windows for a very big slab of memory. And we're like, give us a lot. And then instead of Windows subdividing it somehow into our stuff, when we start function A, we're like, okay, we will put it at the very start over here. When we start function B, we'll just append it over here. And this is very nice because it simply reduces, it increases the chance that the cache will be correct, and it also might decrease the offsets that we have to use when we are jumping between this code. And finally, one real reason why we will have to do this is that if you think about it right now, we are doing all of this at runtime, right? We are just compiling our functions and we are putting them somewhere in memory. But if we want to eventually get to writing out actual executables to disk, this is just not going to work, right? Because in executable, you need to have this kind of packing, right? You need to be able to put all the functions one after each other, and only then, and like this would be the size of your executable. One extra thing to note that if we're talking about executables, so if we say now that this is like foo.exe, so let's say we figured out how to write an executable and we dumped it in there. Executables also need to store somewhere static data. So like big arrays, strings, and so on. So usually you would have your, like, usually it consists of several sections, like you have code, and then you would have, for example, constants, and I don't know, globals. And the difference between globals and constants is just how memory is marked. And this is something we will also jump to in this episode. But the first thing I want to do is, even though we are not doing this just yet, so we are not writing out executables because it will require quite a lot of other preparation, but I do want to make sure that our functions are basically now allocated one after another in memory. And the next thing, if we get to it, it would be to create a concept of constants block or area, whatever you want to call it, in our setup as well. Because right now we don't have really anywhere to put data that we don't want to put in a stack. We could keep it in the main memory of the application, but first of all, it's not really universal and it will not scale to writing out executables. But yeah, so we just want to have this ability to have some constant storage that we can dump things into and get them out. And you saw actually me wanting something like this in last episode if you watched it, where it's like, oh, I wish I could put type info somewhere. I don't want to put it in a stack, but where do I put it? So the place that you put it actually is this area. Okay, so this is the plan for today. I think I can remove the painting stuff for now and jump back into the code. Okay, so what does it mean for us? This means that we would need to have some kind of concept of these regions that we use, and we will need to put them somewhere. Let's open up our value h and think how this is done. So right now, function builder has a buffer which is created with that executable memory that we can put instructions in, and it will be executed. And the only real change here would be that instead of having a buffer on each function builder, we will make it shared for all of them, and it will just simply stack all the functions together. Obviously, we'll need to increase the size of that buffer, but this is all that's going to happen. So let's start with that. If you want it to be shared, we probably want to change it into the buffer, and this will generate a ton of errors, but this is okay because we can fix them. And we also need to think about where does this buffer actually come from, because previously it would just be created in function begin, I believe, but now it's not going to be there. Well, for now, let's just start fixing this stuff. Oops. Apparently I switched the... yeah. Okay. So buffer dot... oops. Mm-hmm. It's good, 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 and good. So that should fix majority of the warnings, except for this one. This is where, as said in function begin, we are actually creating a buffer for all of the functions that we are creating. So like for each of the functions that we're creating. And we need to do something else instead right now. I guess what I would do is I would just pass this as another argument. Buffer star buffer. And remove it from here. So now obviously we have a bunch of errors that are connected with our macro that now needs to be updated to actually get it from somewhere. So we search for define function. And here we need to pass in this function buffer. Okay, what is the function buffer? We don't know what it is. And right now I will basically turn it into a global. So like each test on each round of the testing, we will just create a new one and then we will deal with it. Now, one thing to note is we cannot really easily just reset that memory like we're doing with temp buffer because like CPU considers instructions to be more or less immutable, and if you want to change a region of memory that previously contained instructions, especially instructions that were at some point executed by the processor, you have to explicitly flush the cache of the processor, and I don't want to get into this, so we will be leaking memory right now in tests, but we are leaking it sort of anyway, so it's fine. I'm just going to be leaking a bit more. And I will add a comment saying that that's now the case. Okay, buffer star function buffer. And in before each, what we do is we say function buffer is this stuff. Actually, yeah, it's like this, and then we need to update this to be %. Okay, let's check what is going on. There is still a problem here. Yeah. So these two functions, they don't know where to put their function buffer right now. What should we do with them? I guess I will make it a global. It doesn't really matter for now. It would be better to just pipe it through all the calls, but it's not very important. Builder buffer is like this, yeah. So encoding doesn't really change at all. And if I haven't messed up anything, it should just work, but you never know. One thing that might actually be a problem is that is alignment. We might have to make sure that each of the functions starts at the 16-byte boundary, but I'm not sure that's required. Let's see. Oh, apparently things are very, very exploding. And we can try to figure out why. So one thing might be now that we are simply not fitting into the kilobyte of memory. So let's slightly increase it. Let's say we have 32K for all of this. Or since these are tests, honestly, I don't really care. Let's just leaking a megabyte of memory for every test might not be the best of things, but it's fine. So let's increase this. We are still horribly crashing. So let's see what is going on. And mass solution. Let's check. Actually, I believe I know what is going on. So now how should I deal with it? So one of the issues currently is we were expecting the in function start. Let me function begin. Let me go to there. We are kind of expecting that in the buffer, the first instruction will be at the position 0 of the buffer, but it's sort of no longer the case. So we actually need to either change that or create a new buffer for each of the functions. I mean, new buffer object, not actually different memory, but objects. Either way, we will need to do some synchronization. So I think what I will do is say void star code, whatever. So this would be just a pointer to the resulting code, and that pointer is something that we can initialize right away, and we say code is function type a pack. Actually, we probably can use it here as well. Function type a pack code. Yeah. We cast to this buffer memory plus buffer occupied. So we're basically pointing at the first free byte in the buffer. And then inside of function end, where we were, where is the result? Yeah, so now this will be, so you don't actually need this variable at all, I guess, because this is the place where we create the return result. Yeah, let's get rid of it if you don't need it. It's always nicer to have less things if we realize we do, then that's okay. So this is the only thing that we need to change. We just need to add this offset of buffer occupied to here, I hope. Well, let's see what happens now, shall we? We are still not happy at all. Let's see what's going on. Just one more thing I want to check before diving. So we are creating page execute read write buffer. That's fine. Okay, I guess it's debugger time. I bet it will be obscure access violating writing to location. Yeah, this is roughly what I would expect to happen. Just having an obscure crash in the CPU. Well, I guess we can start by putting a breakpoint and figuring out what is going on. So we create descriptor, we create a builder. Let's look at the buffer. Well, buffer has some memory, it has nothing occupied, and has capacity, so that's okay. What is happening? Ding, ding, ding. And let's check the function value. So function value operand immediate 64. Yeah, this is the same thing. So it points at the right location in memory. That's fine. And are we crashing inside of encode? Yeah. I think I made a mistake when doing this. In builder, buffer builder. Maybe not though. So let's add another thing here as a breakpoint. And right now I'll just let it run because we know it gets to here just fine. This is not really interesting. We know our matching of instruction works. But apparently, so I need to add actually here instead of here. So this is where we are starting to do actual encoding. And I'm interested if it crashes when we try to do buffer append. So I actually need to put it even lower, or maybe even more lower. I guess it's no. Where are we starting to write? Here. Okay. So what is the buffer? So now buffer is something weird. And it already has something occupied. Did I miss where we wrote to it? Strange, but okay. So yeah, writing to the buffer actually works. This doesn't seem to be the issue. Okay. We can encode a bunch of instructions. Make jump patch. Okay, can we run to here? We can. So this is fine. We are now inside function return. Okay, that's good. Damn it. Was a bit too eager. Let's try like this. Okay, so something happens before we get to this thing, but so something happens over here. And what happens over here? Oh, yeah, that's not great. This is not what we want. So at least there is definitely an issue with offsets here. Like now, we will need to save somewhere this first location in memory where we encoded that sub instruction to update. Let me quickly look through if we need to have something else funky done. Not really, but let me check what happens, where it actually crashes. buffer. Well, this seems fine. Yeah, this all seems fine. So it will obviously crash when we try to run this. Yeah. Okay, cool. So we do need to save that location. So let's say that, but we don't really need to be a function. We can just say that it is u8 star stack reservation instruction location. Quite a mouthful of name, but this is what we want. And this stuff is gonna be this thing. And now we will just say function builder, or maybe we call it something else. Maybe we call it, yeah, let's call it code, a bit shorter. And okay. And now in function end, we need to reset it to builder code, or no, it's not occupied. It's so occupied will be a difference between buffer memory and buffer code or builder code. Buffer memory minus builder code. After memory, syntax error, missing semicolon. Yeah. This should be a colon. And here is struct or union left of memory. Isn't it should be builder buffer memory. Okay, well, let's see if that helps at all. Okay, so now we are progressing. Buffer occupied plus byte size is less than capacity. Where is that happening? Tell me, debugger. Okay. So this is happening in function end. We call what? So this instruction that explodes it. So what is builder buffer occupied? Oh, that's doesn't look very good. Ah, yeah, it should be other way around, because this always points to the start and this does not point to the start, or for some functions. Okay, this was a bit of debugging, but we made it. So now we have all the functions going one after each other in memory. And this is pretty nice by itself. But as I mentioned, another thing that I would like to do is have another kind of slab of memory that it will be used for the constants that we are putting somewhere. And I guess I will actually split that part out in a separate episode, because it will cause us to take care of different addressing mode as well. And for today, the last thing I will do is be nice to myself in the future and actually fix the memory leak before we wrap up the episode. So here, we are creating this buffer, but we never getting rid of it. So on every loop, as I said, like, we are leaking memory. Let's fix it. So after each, we just basically destroy the buffer. We say buffer whatever. I'm not sure if we have the functions to do that even. Yeah, we kind of don't. So we have buffer reset, and we don't have a way to do it better. We grab make buffer, so we have make buffer, and we have, I don't know, delete or free buffer. And free buffer would get a pointer to the buffer, and it will just do the opposite of virtual alloc, which is virtual free. So let's do that. Virtual free of, and then I don't remember the full stuff about virtual free, so let's look up on MSDN. Virtual free. Is it called virtual free? Yes, it is called virtual free. So it takes address, size, and what the hell is DB free type? Free type of free operation, following values. I guess address space after various pages are in free state. Value 0 must be 0. So I guess we should do mem release and mem decommit. No, we should use mem release. Yeah, that sounds good. So let's do virtual free. We will put this as the last argument. This probably will be 0, as it says to us to say that, and LP address is a pointer to base address of the region that is free. Okay, yeah, that sounds good. That means we just do buffer memory and release. Okay, so let's put it over here and do free buffer of function buffer. Must return a value. No, it ain't. Let's check this out. And everything is fine. We are not even leaking memory anymore. And since we are not leaking memory, there is something we will need to look into the future, but I will give you a sneak peek. So right now, our memory, if you look in here, we are doing page execute read write, which means that we are kind of, the CPU is allowed to execute this memory and we are allowed to read and write to it. But I think later on we will change this to only be page execute. So we create the original memory, we allow to write to it, and then once we are done writing to it, we are like, okay, now let's just change this to be page execute, because this will prevent other processes from doing bad stuff to us. And I can preview it how to look like for one of the tests. We will need to have this mechanism to do it for each of the tests, but right now that would involve copy pasting. So instead, we will do it for one, and just to showcase to you how this is going to happen. There is this virtual protect call, and this virtual protect is sort of the cousin of virtual alloc that we are using here, and it more or less takes the same things. So I will do call directly. We will need to do something like this: virtual protect, and it is gonna change the protection mode for our memory to something more safe. Okay. What are the parameters? Address, this is gonna be buffer memory. So function buffer memory, and then size is probably 0. Size of region, this means that I believe I can do 0 here, but I'm not certain. And memory protection option is this memory protection constants. So as I said, what I want to do is try to make it the most restrictive things and do it like this. So page execute and then previous. Okay, that built. Let's see if it crashes though. It does not. So this is what we want. And we can test that this thing actually works. We can change this to page no access, and it will probably crash. Apparently it does not. So maybe we do need to specify this size. So what if we say that we want the capacity? So what if we do this way? Okay, now it crashes, but if I do page execute, does it still crash? No, it does not. Okay, so now it works correctly. So this is how we will need to do it. And now you can see this memory protection in action. Again, to give a bit of hint why you want to do this. So imagine that like we are right now creating code at runtime. And that means that we are reading something from disk or from our program or whatever, and we are just telling CPU to execute this stuff. So if we made a mistake somewhere, or if somebody was able to maliciously add some stuff to us, it would be nice if they were not able to overwrite the code once it's done. And this is why you want to change this stuff. Also, when the things are loaded from the executables, this is what is going to be the memory mode that your code will run in anyway, so it's a good thing to prepare for. Okay, I think that will be it for today. In the next episode, I guess I will start working on that constants block of memory, and if you saw a very quick thing, we will need to look into this RIP relative addressing mode, but it will take quite a bit of time, so let's split it up in a separate video. For now, thank you very much for watching, and hopefully see you then.